So we will be talking how to add geospatial data analysis to your data analysis toolbox. So I hope you all do some kind of data analysis, but if you are not using spatial data right now, we will learn how to do it. And why I decided to do the talk, I am not JS or geospatial engineer. That world was completely foreign to me. I was SQL guy building various data platforms at Microsoft and then at Google. But recently I added, and currently I'm working on BigQuery, which is Google's data warehouse. I think one of the most scalable and easy to use, serverless and so on. But recently I worked on adding geospatial analytics to that data analysis, to Google BigQuery. And of course, we had real JS people from Earth Engine helping us who have expertise in the data. And I realized that those worlds shouldn't be distinct. Like, all data engineers should know how to learn geospatial, to use geospatial data, because it's everywhere. You probably have it even if you don't know that you have the data, or maybe you're not collecting it, but you should be collecting it. So we'll learn and nerd. Hopefully we all be less scared. So once you start learning about JS, reading JS papers and learning their tools, it initially looks like everything is completely different. They're talking about some strange words like layers, base maps, bands, features, and I didn't understand what even those means. But don't worry. Those are like SQL Vault versus Python Vault and R Vault. They look different, they use different tools, but we all process the same data. We all use the same processing techniques. And if you understand data, if you understand how that data might be useful to you, it doesn't matter if you're a SQL engineer or R engineer, you probably would find a way to use your data and get meaningful insights from that data. So let's learn the terminology and jargon of geospatial data guys and understand how to use those tools in your normal data workflow. So it's all data. We'll learn what kind of data is there, what data formats, what standards are there, what can I do with that data, what functions are available in my tools, and what tools do I need and how do I optimize performance. So if you understand that those questions about any data, you can use it. So let's talk about types of geospatial data. And all geospatial data is described in something on the Earth. Something physical, something real that happens around us. But there are different ways to describe that data. And the first that comes to mind are probably those maps, like those maps you see, that measure something like temperature on the surface of the Earth or something like that. And that's called raster data. And think about it as you think about bitmaps. It's 2D grid with some measure or some multiple measures that are assigned to every single pixel. That's all, that's it. So it's, and example of that measure can be elevation, temperature, precipitation, population density, or whatever. And you might find word cell, it's the same as pixel in JS jargon. Band is a measure. So if you have RGB band, it has 3 measures, red, green, and blue. So they will call it 3-band bitmap. Don't be scared. And they call null, they call it no data. Otherwise, it's just a bitmap. If you used it in any image processing tool, you know what the data look like. And like in image processing tools, they started with bitmap data, but they gradually realized that for many tasks, it's much more convenient to use vector data. So we switched from bitmaps to SVG. The same things happened in geospatial analysis. So vector data describes the same things, but instead of describing every single pixel, you describe a region over the surface of the Earth, or a specific point at the surface of the Earth. So for example, here we have like 5 areas, North Bay, East Bay, and so on. So they might be described as 5 different rows in a table, and each row has a shape that describes the boundary of each region. And again, you might meet weird jargon, like instead of calling the data a table, JS people will call it layer or feature collection, and they will call each row a feature. Don't be scared. It's the same kind of data that you are using in any tool you are currently using. So property, if you see property, it's just a column. And typically in geospatial data, there is one special data which contains geometry, which describes the boundary of a polygon, the boundary of the region, like North Bay, or coordinates of specific point, like Auckland, or a line that describes a road. Additional types of geospatial data you might need is road network. Just like the vector data we saw before, that also describes lines, but here think about graphs. In addition to lines, we also describe connectivity, like what turns are allowed, which turns are not allowed, which directions are allowed, and various geocoding and geolocation. Those are just mapping between names and coordinates on the Earth. And names can be anything. Think about postal addresses, think about IP addresses. So what data should you use if you are just regular data analysis, doing data analysis for business or anything? And raster data is mostly imagery. And if you're environmental group evaluating deforestation in Amazon, that's the data you will use. You'll have a lot of satellite images, but you probably are using specialized GIS tools, so I will not talk much about using raster data today. Same with road networks. If you are using road network, you are probably building navigational app, or you are building Lyft or Uber. But vector data, I think, should be used by everyone. And luckily for us, it's available in most databases. So if you use PostgreSQL, it has PostGIS extensions. If you use MySQL, it has MySQL Spatial. And the same for, if you are using Panda, there is a GeoPanda that is an excellent package. And the same for R. Almost all the tools can support vector data. And while they're different, they use about the same representation. And vector data is essentially points, just location on the Earth, like our coordinates here. Lines and arbitrary shapes. Or you might be describing collections of those, of course. When we move to computer, we can describe arbitrary curves. So instead of doing arbitrary curves, we just define specific points and replace curved lines with straight lines connected in sequences. And the same thing happens with polygon, like with shapes. How do you describe that data? Describing is just the format I show here is called WKT, but it doesn't matter. Like all different formats are very similar except different encoding. They just provide coordinates. If you have a single point, coordinates of that point is what your data contains. If you have a line, then a sequence of lines of points defines that line. If you have a polygon, that's more complex. We can have a complex shape, and it can have holes. So the most common approach to describe that is by giving a sequence of loops. And there is always at least one loop. The first loop defines the boundary. All additional loops define holes. So here there is one boundary, and there is a hole that doesn't belong to our shape. So that's the second loop here. And there might be like any mix of those using collections, multi-polygons, and so on. So a puzzle, like about polygons, I said that there is one shell and it might have holes. What do we do with that thingy when we have an island inside of a hole? Well, I will not hold it. It's just a multi-polygon. So instead of describing it as a single polygon, we have to describe it as two polygons. One is red polygon with two holes, and one is a simple triangle polygon which just happened to lie within the hole of the first one. You might also encounter Z and M data, where in addition to coordinates, each point has additional data. It might be elevation, which is called Z, because the first one are X and Y, or it might be an arbitrary measure. So it might be convenient when you travel along the line to associate, for example, time with each point. Next question is, we described abstract coordinates, but once we work with the real Earth, where are those coordinates and what are those numbers? And there might be two major answers. One is you are working on a flat coordinate system of some specific map projection, and that's typically called geometry type in PostGIS, for example. In MySQL, it's called projected coordinate system. And the key here is you are working on a flat map in 2D. Another answer is you are working on spherical Earth. Earth is not flat. So whenever you are working on 2D, you might be doing some approximations and some assumptions that might be not always correct. And when you're working on the sphere, that's called geography type in most of the systems. And MySQL is slightly different. It has a single type, but that one works with geographic coordinate systems. When do you use one or another? Of course, it's simpler to work on 2D. Your computer is doing less computations, but you need some experience in how to do it correctly, because all projections distort some of the data. So you do need to know some math to know which projections should I use for each location. It's also becomes hard when you're working on the whole globe. So the easiest thing is to work with geography type. That one, much easier. So that's one of the problems with working on 2D. Like the shortest path between Europe and United States is through Greenland. But if you draw a straight line on a flat map, that goes through France. And that's not the real shortest line. Another problem when you're working with 2D is anti-meridian. So again, if you try to find the shortest distance between Japan and Alaska, if you're working on 2D, you might get an incorrect answer. If you're working on spherical Earth, you will get the real short distance. There are some complications with working with 3D. The biggest problem is that some systems support it less than 2D because the math is simply more complex. But if your system does support 3D, I highly recommend. One thing to be aware of when you're working on the Earth is inverted polygons. So if I describe a boundary between all the oceans and all the continents on the Earth, so I draw a line, but what does that line describe? Does it describe oceans or does it describe continents? How do you know? So you might get inverted polygons, but all the systems support resolving that ambiguity by using some orientation rule. Okay, so that's a single geometry value. And think of it as any data type. So you use integer, string, float data types. So your system, even if you don't know it, most likely has another data type called geometry or geography. And you use it just like any data type. You create a table with the data type, and you put some data into it, just like any other data. So here we have a table with geometry, like first row describes North Bay, so it has a complex polygon. Second row defines Auckland, so it has a single point. So that's what your geospatial data might look like. There is absolutely nothing different from any other type. Okay, so now we know what data we have, what operations can we run with it? And it's the same answer as any other type. We can construct it, just like you can construct string, you can construct geometry value. Just like you can parse string from hex encoded string or any other encoding, you can convert geography type from common formats. And common formats are WKT, the ones that I shown, or GeoJSON, and so on. Or you can format to external representations, and you can measure. So you can measure, just like you can measure length of the string, you can measure area of the geography, length of the string. You can measure distance between two different geography, and you can transform geographies. You can union geographies, you can subtract them and get a new one, and you can calculate relationship between geographies. Do they intersect? Do they have any common point? Does one of them contains another? And so on. So if you want to find, for example, all points in your data set that belong to California, you will use stcontains function given coordinate, like polygon of California and all the points. So note that typically all those functions start with st underscore prefix. That's the convention that comes from a standard. There was a standard body that was very ambitious and wanted to define all the space and time functions. That's S stands for space and T stands for time. Unfortunately, they never came and did nothing with time. So all ST functions are geospatial functions. Okay, so that's I already described. So you can find relationship between different geometries. And that's the most common thing that you will be doing in your geospatial analysis. So you want to find all the, for example, if you're tracking your employees and you have a table with coordinates of employers, and you want to alert all of them who are near California fire. So you might have another table which has coordinates of all the fires going on, and you want to find out who of your employees are within some distance from the fire, whom should I notify? So I'll call stDistance function between employee and polygon that describes a fire and find out is the distance with less than 5 miles. Then I need to call them. Okay. So that's an example. Let's find census tracts. And that's very common when you do any location analysis. You want to use census data because that's the most detailed data about population that you have. So our table might have, for example, geography ID, just government string that defines that point, name of the tract, and geometry of the tract. And geometry is a polygon that describes particular area, statistical area that has aggregated statistical data about population. So that's actually a subset of data from public table in BigQuery. And we want to find all the tracts that are near Auckland. So we start the same, select tract name and geography, and then we need to find which tracts are within 1 mile of Auckland. So our condition will be st distance between tract geometry and point that describes Auckland is less than 10 miles. So that's distance 10,000 meters, 10,000, and that's miles to kilometers multiplier. One thing to note that argument of geoc point, in geography world, you usually pass latitude first and longitude second. In most SQL systems, you pass longitude first because that's your x coordinates. How does your database execute that query? Just like with any other data, indices are important. And different databases implement indices in different way. There are quad trees, there are R trees, BigQuery uses Hilbert curves. But those indices allow the database to partition geospatial data and quickly find locations that are near specified points. For example, in previous query, we needed to calculate distance between a complex region and particular point. That would be very expensive to do. But most of the systems implement some kind of index. It doesn't really matter which one your system implements. Just make sure that if you're doing those kind of queries and your system requires explicit indices, create those indices and you'll be fine. And just like any other system, it's very common to do joins. Like you are doing joins on some IDs or strings with your integers or strings. It's very common to do joins on geospatial data. And here is that example of finding employees who are affected by the fires. You might have a huge table of employees, and you might have a table with the list of fires. So you're joining two tables, and you're writing the same query that you normally do, with only condition here will be ST intersects. For example, do those regions have any common point? Or another most common condition is STD within. And STD within is the same as distance between two geographies is less or equal than the third parameter, distance. It just on many systems using STD within will be faster. Okay, let's do some demo. So let's construct that query about, I want to learn something about Auckland. So so I'll use find census data about California. So that is list of census tract. That's BigQuery UI. Don't be alarmed if you don't know, but it's just SQL editor. So we need to find something from California census tracts where we are close to Auckland. Yep. Okay. So then we find Auckland in California, and Wikipedia has coordinates. We copy those coordinates, decimal, and paste them here. And as I said, we need to reverse order of the arguments because SQL systems. Yep. So, okay. And it should be less than, let's say, 1 mile. Okay. So that's the most simple geospatial query you have. Unfortunately, it returns just tons of data. So what can we do with it? And you usually find some visualization tool. And here I'll use visualization tool that comes with BigQuery. But most other systems have similar, more complicated and better tools. So the query I have here also joins it with more census tracts with actual data, and I might be able to color it. So that's where color comes, but let's, I think, stop here and take questions.
All righty, does anybody have any questions?
So are there any limitations, like with the geo support you'd get out of, BigQuery or other databases, like when you compare that to, I guess, like ArcGIS? Like, I've never used any of those systems, so it might be a silly question, but like, are we limited in some way with the out-of-the-box support in these databases?
Yes. ArcGIS is, like, I don't know, 20 or 30-year company. They have way more extensive support for various geospatial functions. In BigQuery, we added geospatial support. It was released about a year ago. It doesn't implement the long tail of functionality. We think we implemented the 80% that most data analysts need, but definitely if you are if you are a hardcore JS user, you might find that some of the things you are used to are not present there. We think for those 80% we get much better performance, much better cost efficiency, and so on. But yes, it's nowhere as complete as the whole functionality that exists in ArcGIS.
Alrighty, and this will be our last question.
So you mentioned in BigQuery it is using Hilbert curves. So can you please explain how does this indexing work for these queries for BigQuery?
Yeah, so the question was how does BigQuery uses Hilbert curves? Let's return to that slide. So all those indices allow you to find points that are near specific point. And Hilbert curve, for Hilbert curve we use S2, which is open source code released by Google and used by most of the Google spatial products like Maps, Earth Engine, and so on. It supports that Hilbert curve, and Hilbert curve allows you to map every coordinate or region on the Earth to a single integer. So any position on the Earth within a couple centimeters can be mapped to a single 64-bit integer. So that turns a 2D search space, like the thing why we needed quad tree or why we needed R3 is because we have multiple coordinates. So Hilbert curve turns 2D index into 1D index. Instead of searching in 2D space, we need to find all the intersections of linear range.
Alrighty, and that is the end of the session.
Thank you.